Hello, everybody. Today we are continuing our discussion with acids and bases and solutions. So, today we are talking about something called acid base equilibria, and we'll also talk about solubility and how it also ties into equilibrium as well. So, we've looked at acids and bases. We've looked at equilibrium. So now we're kind of going to put them together. And what I mean by that is we're going to look at what happens when acids, bases, as well as acids and bases get into a solution, right? What kind of equilibrium and what kind of calculations and what kind of compounds and characteristics come out of those combinations. So without further ado, let's get started. So we're going to start with acid base equilibrium, and actually let's start with something called a common ion effect. What is a common ion effect? Well, the common ion, right, the common ion effect is the shift in equilibrium that is caused by the addition of a compound having an ion in common with a dissolved substance. Now, if you remember, what does this sound like? It sounds like Le Chatelier's principle when we talk about equilibrium, meaning that whenever you add something to a solution is going to change the equilibrium in order to kind of counteract that change, right? So what do I mean by that? If you have, find my pen right here. So if you have some like, let's do NaCl, right? You have NaCl, right? A solution of NaCl will be Na plus Cl minus, right? So if you add in this solution of NaCl, right? Think about it. If in this solution of NaCl, if you add something like magnesium chloride, MgCl2, right? Look at what happens. We're adding magnesium plus 2 chlorine here, magnesium 2 plus 2 chlorine ions. So this chlorine right here is a what? It's a common ion. It's a common ion, right? So a common ion when it comes to acids and bases, right? And by the way, we're talking about acids and bases, especially weak acids and bases. Why? Because weak acids and bases are the ones that go through equilibrium, right? They are reversible, if you remember correctly what we learned. So a weak acid gives H plus A minus. We already know that, right? So the common ion effect is telling us that if you add, and I want you to think about this, right? If this is the common ion, A minus, right? And then you add it. Let me say like I add Na plus A, right? So if I add this into the solution, that means that I added more of A, right? If I increase A, what direction does my reaction go to? If I increase A, does the reaction shift to the right or to the left? It's gonna go this way, right? It's gonna go this way to reduce this change, this increase in A, right? So that's what they mean by when they say that the presence of a common ion suppresses the ionization of a weak acid or a base. So when you add a common ion here, it's going to go back. Instead of continuing to do the ionization, it's going to go to the opposite way. So that is the common ion effect, and I want you to understand that because we are going to get back to the common ion effect, right? When it comes to some sort of calculations. Now let me introduce you to something else. This is called buffers. Now we love buffers. We use buffers a lot in lab, and guess what? Our body contains buffers. Buffers are these systems, right? Solutions, right? First of all, before I say what they are, they contain. The definition of buffers is a solution that resists pH change when an acid or a base is added. Usually when you add an acid or a base to something, it changes the pH like that. But for buffers, they resist that change. So the definition of a buffer is a solution that resists changes to pH when an acid or base is added. And I want you to know why. Why does it resist changes? Because a buffer is going to have two things, right? It's going to have a weak acid or a weak base, right? So a buffer is going to have a weak acid or weak base, a weak acid or a weak base. So it will have a weak entity, and then it's going to have the salt of that weak acid or weak base. So it will have the conjugate. And in the buffer, you have to have both. It's very important, guys, right? So and a lot of people confuse buffers as acid or base, but no, a buffer is going to be a mixture. A buffer is a mixture that has two things: a weak base and its conjugate acid all together. So if you look at this, and I want you to see the difference, because it might seem similar, but if you look at this, right? So usually we say, okay, an acid is HA that gives me H plus plus A minus, right? This is a weak acid, right? This is a weak acid. A weak base is B that gets H plus, and then reversible BH plus, right? So this is a weak acid. This is a weak acid, WA. This is a weak base. A buffer is something that will contain both a weak acid and its conjugate base, or something that has both the weak base and its conjugate acid. So a buffer system will contain two pairs, HA and A minus, or B/BH plus, right? That's the difference in the buffer. Very, very important. So an example is CH3COOH is a weak acid, and then CH3COO minus is a conjugate. This is an example of a buffer pair. Example of a base buffer pair is NH3. If you remember, NH3 is a weak acid, and then NH4 plus is its conjugate. It's a weak base, and then this is the conjugate acid, right? By the way, these, because they are in solution, sometimes in addition to, instead of being ions like this, we can have like CH3COOH, and then it's going to be CH3COONA, right? It will be bound to sodium. Don't be intimidated by sodium. It's still COO minus. It's still a buffer system, right? Or sometimes this one is going to be NH3 and then NH4Cl is just because NH4 is not by itself to begin with. Is still a buffer system, right? So a buffer system, it will have those two pairs. Very important to remember. This is another example here, right? Telling you like, hey, now these are two examples, but let me show you because I say that I will show you. I'm going to show you what happens when you add a strong acid or a strong base to a buffer. And you might already have guessed it, right? A buffer has an acid entity and a base entity, right? Here, same, it has a base entity here and an acid entity here. So what ends up happening is that if you add an acid to your buffer, the base entity will neutralize it. And then if you add a base to your buffer, the acid entity will neutralize it. Remember, neutralization is when an acid binds to a base to form water and salt, so to basically neutralize it. So this is what happens here, right? If you have a buffer that has acetic acid and sodium acetate, these are the two buffers. This is a good common buffer that we make in the lab. Then look at this. If you add a strong acid to this buffer, this is what happens to it. The base, the conjugate base, takes care of it, right? If you add a strong base here, guess what? The acid takes care of it. It's gonna give it its hydrogen here, and then you get this plus H2O, right? So one of my favorite questions to ask, and a question that a lot of people are going to ask, is if they give you a buffer system, they will ask you like, hey, if I add a strong acid to this buffer system, what happens? If I add a strong base to this buffer system, what happens? And you gotta know that it is going to be taken care of. The acid is going to be taken care of by this basic entity in the buffer, and then the base is going to be taken care of the acidic entity in the buffer. That is where the definition of buffers come from, right? This is how they resist the changes to pH. This is how they protect your blood. The blood contains a buffer system, and it protects your blood from your blood pH from changing too drastically, right? Very, very important. Now we need to know how to calculate the pH of buffers, right? The pH of buffers is very different, and I'm going to give you an equation. Don't worry about all of these. An equation called the Henderson-Hesselbalch equation. The Henderson-Hesselbalch equation is going to be, right, this is how we find, so this is what you're going to remember. Make sure that you write it down, right? This is an important formula. The pH of a buffer is going to be equal to pKa plus log of your A minus over HA. A minus and HA being what? Being our, so remember, HA gives you H plus plus A minus, right? And these are two entities that we have in a weak acid buffer, right? In an acid buffer. So these are the two entities, the acid and then the conjugate base, right? So pH is equal to pKa plus log of A minus over HA. The pKa is a constant, right? The pKa comes from Ka, the dissociation constant of this acid, right? So pKa is actually equal to negative log of Ka of that acid. So this right here, this equation, if you're being introduced to it for the first time, make sure that you write it down. It's called the Henderson-Hesselbalch equation. Very important, very many implications. And then again, this is the pKa, right? So if you have water, right, and you add acid to it, the pH of water is going to drop, boom, significantly. Like, all you need is a drop. I've done this before. I've had water where I added like 1 drop of acid, boom, the pH goes all the way down. But if you have a buffer, the pH doesn't go down no matter how much. It takes a long time to change the pH of a buffer. But again, that's how we calculate the pH, right? So I can ask you, like, which of the following are buffer systems, right? So KF and HF, do you think it's a buffer system or not? Think about it, right? HF, is it a weak acid Is it so HF is an acid, right? Is it a weak acid? Yes, is a weak acid. Now KF is the the conjugate of that acid. Yes, because it has F minus. So HFKF is a good buffer. Yes. All right. So what about KBr and HBr, right? HBr, is it an acid? Yes. Is it a weak acid? No, HBr is a strong acid. It cannot be a buffer because buffer has to be weak, right? All right, how about this one? Sodium carbonate and then Na2CO3, NaHCO3. None of them are. So let's see. CO 3 2 minus, so I'm just going to remove sodium, right? And then it's HCO3 minus, right? Now these two, right, one is a weak acid, the other one is a conjugate base, right? So these two are a good buffer pair as well, right? So I'm going to give you a bunch of pairs in the future, and then I'm going to ask you like, hey, what, like, is this a buffer or not, right? But then after that, I'm gonna ask you like, hey, what's the pKa? And don't worry about let's not worry about the way they are doing it here, right? Let's not worry about the way they're doing it here. Let's see. Hold on. Yeah. Okay. Let's do it ourselves, right? So it said calculate the pH, right? They calculated the pH, and then they gave you a buffer system, right? The buffer system has two things, and then they're asking you what is the pH. Ooh, what is the pH after the addition of 20 milliliter of 0. molar NaOH to 80 ml of the buffer solution? Oh, this is a fun one. This is a fun one, but it kind of puts everything together that I want you to know. So let's do it together. All right. So first of all, what's the system for our pH? Is the system a basic pH, a basic buffer, or acidic buffer? It is a basic buffer because NH3 is a base, NH4Cl is its conjugate, right? So the reaction goes like this: NH3 plus H plus, right? Or H2O, right? Let me just give it H plus, right? Becomes NH4 plus, right? This is my buffer, right? This is my buffer. Now they're telling me that this has 0.1 molar, this has 0.36 molar, right? That is the starting point. Now that we have the molarity, let me ask you this: what is the pH of this entity, right? What is the pH of this entity? Now let me show you something, and this might be I'm trying to see if I can find the pKa. Yeah, okay, the pKa. I have the pKa of the pKa first, right? I have the pKa. So the pKa is 9.25. pKa is going to be given, right? pKa is going to be 9.35, right? So there are a few ways to do this. But again, pH, if you remember, is equal to pKa plus log, right? Log of the conjugate, right? So in this case, the conjugate is this. No, log of the acid. Log of the acid. Not acid, the base. What am I doing? The log of the base over the acid, right? So kind of like here, NH4 plus, right? Here we had, what did I do? So here in an acidic system, you have the base at the top and then the acid at the bottom, right? But in a basic system, we're just going to do the same thing, right? Base at the top, acid at the bottom, right? So this is going to be equal to pKa is 9.35. So you're either going to be given pKa or you're going to be given Ka. And if you're given Ka, remember that pKa is negative log of what? Of Ka, right? So pH is equal to pKa plus log of NH3, which is 0.3 molar, over the other one 0.36 molar, right? So you work it out here, you figure out that the first pH, they calculated this here, 9.17, right? The first pH is 9.17, right? So this is the pH of our system. This is the pH of our system. So we use the Henderson-Hasselbalch equation very, like when it comes to buffer, we use it very frequently. But again, if you have you can use it for your acid buffer or your basic buffer, as long as you remember pH is equals to pKa plus log of A minus, which is the base, over HA, which is the acid, right? But if you have a basic buffer, it can be, which is B over BH plus, right? So remember this, it's very important, right? Now, after this, the question makes another plea. It tells us that what is the pH after the addition of more of NaOH to the buffer? All right, so I want you to work with me here, okay? So if we add NaOH to this system, what's gonna happen to it, right? Remember, when you add something, it's going to be taken care of by either the base or the acid entity, right? This is the base entity, this is the acid entity, right? So if you add NaOH, what's going to neutralize it? Is it the base or the acid? NaOH is the base, right? It's going to be neutralized by our acid, right? It's going to be neutralized by our acid. Now, when it gets neutralized by our acid, is our acid going to go down or up? The acid is going to go up, down, because it's being used up, right? It's being used up. The NaOH is going to come here. It's going to use up our acid. So our acid goes down. So I'm just going to put this concentration will go down here, right? And then guess what? When our acid is used up, our base goes up, right? Because it's going to go that way. So our base is going to go up. So acids go down, base goes up. And guess what? By how much is it going to go? By how much is it going to go down? Because our task right now, we already calculated the pH with these molarities, right? So our task right now is like, okay, how are these molarities going to change in order to get a new pH? So now I know that this molarity is going to go down, this molarity is going to go up, right? So when you add, a rule of thumb is when you add a base to a pH, when you add a base to a buffer system, the base entity goes up. When you add an acid to a buffer system, the acid entity goes up because the base goes down, all right? So again, you add NaOH, that means the NaOH is a base, so the base entity goes up, the acid goes down. By how much? It goes down by the number of moles, of what was added. So they added 20 milliliters of 0.05 molar NaOH, right? How many moles is that? If you remember your formulas correctly, molarity is equal to moles over volume in liters, right? So the moles, N, is equal to molarity times volume in liters. All right, so it's going to be equal to, what's our molarity? 0.05 times volume in liters. Volume in liters is going to be milliliters over 1,000, right? So it's going to be 0.05 times 0.020, right? 0.001 moles, right? And it should be the same that they calculated, right? So 0.001 moles is what we're adding. 0.001 moles is what we're adding, right? So unfortunately, this is okay, but in order for us to, so these number of moles is the moles of NaOH we're adding to our solution, our system. So that means that NH3 will increase by 0.001 moles, and then NH3 plus will decrease by 0.36 moles. Well, in order to subtract, we cannot subtract from molarity, right? We have to turn this to moles as well. But guess what? They gave us the milliliters of solution, right? Milliliters of the buffer solution, that's the total volume. So we're going to use the same formula to convert this molarity into moles, right? Which is so molarity times volume in liters, right? So our 80 milliliters 0.8, right? So it's like 0.1 times 0.08, right? So this right here is going to be equal to 0.008 moles, right? And then here is going to be how many moles? 0.36 times 0.08 is equal to 0.029 moles, right? So you have these moles, right? So originally we just converted this concentration to moles, right? So originally we have these many moles, and then we already say that this goes down, right? The acid side goes down, the basic side goes up. By how much? By these many moles, because those are the moles we adding of NaOH, right? So we're just going to find the new number of moles, right? The new number of moles will be equal to, look at that, we take this, since this goes up, I'm going to take this plus 0.008. It should be 0.009 moles, right? And then this one goes down by how much? By this much, right? So it's going to be 0.028 moles, right? So this is the new number of moles. So we took the concentration, we converted into the number of moles so that we can see how the number of moles changes when we add something to our buffer system, right? Very important lesson, because now after we have this, we can convert it into molarity. How do we convert it into molarity? Well, this formula right here, molarity is equal to moles over volume in liters, right? So I'm just gonna take the moles over the volume in liters, right? And what's the volume in liters? It is 0.08, right? So you remember that 0.08, right? So it's going to be 0.009 over 0.08. And now the new molarity is, drum roll, 0.1125 mole, right? And then here, same thing, molarity is equal to moles over liters, right? Which is 0.028 over the liters, which is 0.08. That's 80 milliliters. So this is going to be not over. It's going to be, it is over, right? Moles over liters, 0.08. Okay, 0.35. Okay, what? Moles. Yes, it is 0.35. Okay, I was wondering why it's high, but it started at 0.36. So as you can see here, our new molarity, right, is, it has gone up here and then it has gone down here as it should. And now that we have the new molarity, guess what we can find? The new pH, right? So the new pH is going to be equal to, again, pKa plus log of the base over the acid, which is equal to pKa is 9.35 plus log of the base, which is 0.1125 over the acid, which is 0.35, right? And this is the new pH, and it should be the same here, which is 9.2. Wait, let's double check here. Very interesting. They got a different number of moles to start with here. I don't know why. Wait, we got the same number of moles. Same number of moles. If we add NaOH, let me double check. So if we add NaOH to the system, and the acid goes down, yeah. Ooh, the acid goes down. Okay. The acid goes down, and this, it went down here, yeah. Okay. It did go down. Okay. Start moles, end moles. Okay, that's good. What about the other one? We start with 0.1. The end moles is 0. No, the end moles is not 0. This is gonna go up, right? So I think they did it wrong. They did it wrong. I don't believe it. Okay, so they did this side right, but they didn't do this side right. So we are going to go with what I mentioned, guys. So we're going to go with this one. I think we did it correctly, right? One side goes up, the other side goes down for sure. All right. So one side goes up, one side goes down, and then we find the new molarities, and then we just calculate the new pH. All right, so now we have a new pH and an old pH, and let me go ahead and calculate it. All right, so log of 0.112 over 0.35 close parenthesis plus 9.35 is equal to 8.85, right? 8.85, right? All right, so that is again two very important lessons. One easy, one hard. The first important lesson is, how do you find the pH of a buffer? And that is easy because I gave you the formula. You gotta remember it. Make sure that you remember it. Is the formula is pH, right? pH is equal to pKa plus log of the base, right, over the acid. Let's just say this, of the base over the acid, right? And one will be a conjugate, one will not be a conjugate. So here base over the acid can be A minus over HA in an acidic buffer, or BH no, this is base is B over BH plus in a basic buffer, right? That's the first important lesson. The second important, sorry, I thought I was showing you, but this is what I was showing you. Okay, so pH equal to pKa plus log of base over acid, right? And then base over acid here will be, in case of an acidic buffer, it's going to be this. In case of a basic buffer, it's going to be this, right? It's a very important lesson to remember, right? Second lesson to remember is, we need to remember what happens to the pH when we add an acid or base. Because guess what? When you add an acid or base, this concentration changes and this concentration changes, right? And depending on what we have, so this is a weak acid giving you this, right? Or a base, depending on what system we have, right? And depending on what we're adding, one of them will go down, another one will go up, right? For example, in this acid system, if you add HCl, for example, right? If you add HCl, we are going to work in a way to counteract that acid, right? And if we're trying to counteract that acid, we are going to use up our base side, right? We're going to use up our base side in order to counteract the acid. So we're going to go that way, right? Meaning that this is going to go down, this is going to go up, right? So that is the second lesson that everybody needs to know. And I will definitely ask you a question like, hey, what is the pH of this buffer? That will be easy. A little bit harder will be, hey, if I add these many moles or these many liters or these many grams of an acid or a base, what happens to that pH? All right, so make sure that you take time to practice these types of questions. Now I'm gonna pivot to something more fun. It's called titration. You probably have seen this. Many of you all have actually done this in the lab. And titration is an act of titrating or adding, right? Adding gradually, right? Titration is adding gradually. That's what titration is, right? So you add an acid or a base gradually to another, to a base. So you titrate an acid to a base, or a base to an acid, right? It can be a base to an acid. And you're gonna have a burette. Burette is going to be titrating in here. And then when we titrate, this is an experiment that you've done before, right? You add an indicator in your acid or base at the bottom, so that when we reach equilibrium, when we get to a place where, when we reach equivalence point, we get to a place where we neutralize all the acid or base, the indicator changes the color, right? So we want to catch that pink color right here, right? To catch the change, to catch the equivalence point. Why are we doing this? We're doing this in order to accurately, so to find an unknown concentration, right? So if you can titrate a known concentration to an unknown concentration, reaching the equivalence point will tell you the volume it takes in order to titrate that much, and that volume will give you the concentration of the unknown. And if you remember, I gave you a very easy, if you have like an easy acid-base reaction like NaOH plus HCl, which gives you NaCl plus H2. This is the neutralization reaction, by the way, because we take a strong acid, strong base, we become salt and water. pH 5 changes the indicator, we stop, right? So since one NaOH reacts with one HCl, this is a 1-to-1 reaction, means that 1 mole of NaOH will neutralize 1 mole of HCl. And if we have that, we can just have this formula: MAVA is equal to MBVB, meaning that the molarity times the volume, the molarity of the acid times the volume of acid is equal to the molarity of the base times the volume of the base. This only happens when you have a 1-to-1 relationship like this, but that is how you can easily find the concentration, right? Now, there are things that we call titration curves. You can titrate and measure pH. So you can titrate NaOH and HCl and measure pH, and look at what happened, right? When you're adding NaOH and you're measuring pH, the pH is gonna go up, right? Because NaOH is basic. And look at this, it goes up slowly until it reaches what we call the equivalence point, and then it jumps up high, and then it continues here. The middle here is what we call the equivalence point, and the pH is around 7, because again, NaOH and HCl will give you a neutral curve, right? It will give you salt and water, which are neutral. Everybody with me? This is what we call a titration curve, and this is easy when it comes to strong acid and strong base. But look at what happens when you add a strong base to a weak acid, right? It's going to still keep going up, but guess what? The equivalence point will not be at 7. Because you have a weak acid, the equivalence point will be above 7, right? It will be above 7. So this will, and it will kind of have a bend up here. For a weak acid, it has a bend up here, right? And this is what we call the Ka, right? But the equivalence point, the point that I'm making here is the equivalence point when you titrate. So when you titrate a strong acid to a strong base, equivalence point is at 7. When you titrate a strong base to a weak acid, the equivalence point is at 7. As you can imagine, it's weak. The acid is weak, so you go into the NaOH brings the pH up higher, right? Now, what if you do the opposite, right? What if you titrate a strong acid to a weak base, right? And as you can see here, the pH is going down because you're adding an acid. When you add acid, it lowers the pH, right? So you have a weak base here, goes down, and again, the equivalence point will be below 7, right? Will be below 7 because you have a strong acid to a weak base. If it was a strong acid, strong base, it will be 7, but because it's a weak base, it's below 5, right? Below 7. So this I will also ask you. I will be like, hey, if I am titrating a strong acid to a weak base, what will be the pH? It will be at 7, below 7, something like that. So make sure that you know about these titration curves and what they mean. They will definitely come back. Even in my biochemistry classes, I teach titration curves, right? We love titration curves. All right, so this is how they ask you, like, hey, if we add 100 ml of 0.1 molar HNO3 with 0.1 molar NaOH, what is the pH at the equivalence point? All right, so let me mix it up first, right? Because I don't want to confuse you. If I asked you, right, first, like, exactly 0.1 molar of HCl, right? HCl are titrated with 0.1 molar NaOH. What are you going to do, right? If you have 0.1 molar HCl, you're going to be like, oh, HCl, I know HCl plus NaOH is just a very simple H2O plus NaCl. This is a neutralization reaction. It's a 1-to-1. They gave me the concentration of one. They gave me the concentration of the other, right? They gave me the volume. I don't even need to search the pH. Why do I not need to search the pH? Because I know that the pH at equivalence will be 7 because both of them are strong. The pH at equivalence will be 7 because both of them are strong. But if you have HNO3, which is a weak acid, right? Remember, it's a weak acid. If it was HNO2 is a weak acid. If it was HNO3, it will be a strong acid, but HNO2 is a weak acid. So you're titrating a weak acid with a strong base. So the pH at equivalence point, right? We know that that pH will be above 7, right? We already know that. But in order to find that pH, guys, we need to kind of chase how much we are changing, how much is changing the concentration, right? So let's do this, right? So you're starting with these many moles, right? With HNO2, right? And then you're adding these many moles of NaOH, right? And then at the end, you're going to end up with, after titration, you're going to end up with this many moles of NO2, right? This is what will be our conjugate base, right? This is what happens. Now, if you have this many moles, right? And the final volume is 200 ml, right? Then you can find the molarity, right? The resulting molarity of our product, which is this, right? This is the resulting molarity, right? And here, the missing piece, they should have told you exactly 100 ml of NaOH are titrated with. Well, I guess they assume that you would know, but you don't have to know. If it's going to be 100 ml, so they are titrated with this much solution. It's going to be 100 ml, right? 100 ml. So the way I found this, by the way, is just like 100 ml times 0.1 over 0.1, right? So this still MAVA is equal to MBVB, right? So we found the volume of this solution by just doing the multiplication, right? Because this multiplication has to be equal. So I found 100 ml. So you have 100 ml of NaOH, you have 100 ml of HNO2. That's why the final volume is 200. So we cannot use this concentration. We gotta use the concentration of the total volume to get the concentration of our product. So this is the concentration of our product, right? This is the concentration of our product, and we need to find the pH of this. But the problem is, again, if you remember how we find the pH of weak acids and bases, how do we find the pH of weak acids and bases? The ice table. I know it's the ice table. It's coming back. So the ice table is going to be, you have the concentration, you have 0, 0 here, right? And then you say minus x plus x plus x. If you remember, we did this one, this one at equilibrium. Then you say Kb, or the equilibrium constant, is equal to this, x over 0.5 minus x. And then we're going to do the approximation. If you remember, this is the approximation that we assume so that we can find x equal to this, right? And then the x that we get, guys, this is actually important. The x that we get when we have a base system, the x that we gave, if you can see, the x is the OH minus concentration. The x is the OH minus concentration. Why is that important? We cannot find pH with OH minus concentration, but what can we find? We can find the POH, right? The POH is equal to negative log of OH, and then from the POH we know that the pH is equal to 14 minus POH, right? So that is how we find the pH when it comes to titration, right? Very, very important. Let's talk briefly about indicators. How do we find the right indicator, right? They also, indicators, for them to change color, they also have acid-base reactions. I won't get too much into it, but just know that different types of indicators with different colors have different ranges. So you see at the pH range, you have different pH ranges. So depending, right? For example, this equation that we just looked at, we just saw that the pH at equivalence point is 8.02, right? Well, if you want to choose what indicator to choose, which one would you choose? 8.02. That's right, you're gonna choose this one, right? Because everything else will not fall into that. So you choose the indicator based on the pH range of the, no, you choose the indicator based on the equivalence point pH, so that you can find the right range, right? And we like these ones. We like phenolphthalein and methyl when it comes to titrating strong acid and strong base. But if you're titrating something else, you're gonna use a different indicator, right? So I can ask you a question like that. This is what I just talked about. I can ask you like, hey, what indicator we're gonna use based on what we are titrating, right? So now I'm going to talk about something equally important but different from acids and bases, and this is what we call solubility. And we did talk a little bit about solubility before, but now we are kind of adding numbers to it, right? We said things are soluble in water, insoluble in water, they can dissolve, they cannot dissolve, and things like that. And usually things that dissolve in water give us salt, right? If you remember, you can add NaCl, right, which is a salt, right? NaCl is a salt, is solid, becomes Na plus, and it's aqueous, right, in water, plus Cl minus, which is aqueous, right? So as you can see, you have solid gives you aqueous solution, and that's important because there is equilibrium when it comes to solubility. What do I mean by that? If I take AgCl, this is another salt that's solid, gives you Ag plus with Cl minus, right? The solubility product constant, this is a constant that has to do with solubility, is going to give me to be the product of these products, right? It's the product of the concentration of these products. We don't include the what, we don't include the original because it's solid. So So when it comes to KSP, or the solubility product constant, we only use the products. So these are examples. Look, MgF2 becomes Mg plus times 2 plus 2F. What's going to be the KSP? It's going to be Mg2 plus F squared. Y squared, remember that we count the coefficients when it comes to equilibrium. This is another type of equilibrium constant. All right, so what if you have Ka3 and PO4 2? Well, they give you 3 Ka2 plus 2 PO4, and then the KSP is going to be Ca equals to Cl2 plus 2 cubed times PO4 3 square, right? This again is what we call the solubility product constant. Now, so this only happens at equilibrium. So this is at equilibrium. But if you are not at equilibrium, you can use different concentrations, and we're going to have Q, which is just a product of the concentrations at just a random concentration, not at equilibrium. So if Q, look at this, if Q is equal to KSP, you have a saturated solution, it's liquid, right? If Q is under KSP, you have an unsaturated solution, it's also liquid, right? Both of these are liquid, no precipitate. But guess what? If Q is over KSP, you have a super saturated solution and you will form a precipitate. Why? Because Q being over KSP shows you that you have way more product than is soluble, because KSP the solubility constant. So if Q is over KSP, you have more product than it is possibly soluble, and that will form a precipitate. So when we get to calculate KSP in a minute, we'll be able to tell whether something will form a precipitate or not. So these are examples of different KSP. Each one of the salts will have a different KSP, and it will inform how much you can add in a solid, for example. Now, how much solid you can add in a liquid for it to not be a precipitate, right? Now let me introduce you to two other terms. Molar solubility, right? So the one that I just introduced you to is called the solubility product constant, right? The solubility product constant. But then you have solubility itself. So you have molar solubility, and then another solubility is usually like pure solubility is grams per liter, right? Which is basically the number of grams of solute that can be dissolved in 1 liter of a saturated solution, right? That's solubility. Molar solubility is in moles. It's exactly what the same, but it's in moles. So it's the number of moles of solute dissolved in 1 liter of a saturated solution, right? So you have molar solubility, you have solubility. So if you have a solubility of a compound, which is grams per liter, this is showing you how you can convert things, right? If you have a solubility of a compound, which is grams per liter, you can turn it into solubility, molar solubility, which is mole per liter. How are you going to turn it into? You should know, because to go from grams to moles, what do we use? We use the molecular weight from the periodic table, right? And then from there, you can then use the concentration, right? Remember, mole per liter is also concentration, right, of cations and ions, right? So mole per liter as well. And then the KSP will just be the product of that, right? KSP will just be the product of those molarities. And you can go the other way around, right? Go from KSP to anions to molar solubility and solubility. So this is kind of showing you the blueprint of how to solve some of these problems, right? So let me give you an example. I might ask you like, hey, what is the solubility of silver chloride in grams per liter? So what is the solubility? and then they gave you the KSP. So what is the solubility? So, and you might not seen this before. So again, when it comes to solubility, we only care about these, right? Because this is the powder. AgCl(S) is the powder. It doesn't get dissolved. Whenever it gets dissolved, it turns into this. So at the beginning, initially we have 0 for both of them, right? And then the change is the S, the solubility, right? The change is the S, and then it adds for both of them. Remember, if we had a coefficient, it would be like 2S or something like that. And then at equilibrium, you have S, right? So KSP, right? KSP, which they gave us, is the concentration of Ag plus Cl minus, which is going to be equal to S times S, which is S square, right? And guess what? KSP, S is going to be equal to the square root of KSP. We already have KSP up there, so this is S, right? Why do we care about S? Because S is a concentration of Ag plus and then concentration of Cl minus. So S is the solubility, is the molar solubility, right? It's the molar solubility. And in order to go from actual solubility, which is grams per liter, we're going to turn our moles into grams. And if you remember correctly, we turn our moles into grams by multiplying with the molecular weight, right? So this is the molecular weight. So we went from moles per liter to grams per liter through the molecular weight. So this is the solubility. Solubility, this is the S is the molar solubility, right? Molar solubility. And then again, this is the molarity of the two. So we just did this, right? We were given KSP, and from KSP we found the concentration of the cation and ions. We found the molar solubility, which is S, and then from there we converted it into solubility, which is grams per liter, by multiplying by the molecular weight. So we use the molecular weight here, and then we use the ice table here. Does that make sense? So again, as you can see, it's still using equilibrium. That's why I was telling you, like, hey, the ice table, we're gonna use it a lot. As you've seen, we've used it with acids and bases, we've used it with salt, we've used it with equilibrium constant. We use it a lot, right? But again, make sure that you know. And an example, you can use this as a cheat sheet, right? If you have like Ag2CO3, for example, we have 2S, right? Because it's Ag2 is 2S and then S. And then the KSP is going to be equal to that. So please don't memorize this. Please don't memorize this. Just figure it out by setting out the nice table like that, right? You should be able to do that very easily, right? For example, Al Can you hear me? So just as I was talking about how I will ask you like, hey, what's the pH of this? And then I will ask you like, how does the pH change when you add an acid, or how does the pH change when you add a base? Is the same story with this, right? I can ask you what's the solubility of this, and then I can ask you how does it change when you add this common ion, right? And when it comes to pH, the presence of a common ion decreases the solubility. We already seen that, right? And then insoluble bases dissolve in acidic solutions, and then insoluble acid dissolve in basic solution. This is actually very important. We use this in the lab as well, right? So a common ion is going to decrease the solubility, but acidic solutions, if you have an insoluble base, you can add an acid and dissolve it, or if you have an insoluble acid, you can add a base and dissolve it very easily, right? So an example here is magnesium oxide, right? Magnesium oxide dissolves in water, right? And this is its solubility. You can find the solubility here, right? And then from this you can find OH. From the OH you can find the POH. From the POH you can find the pH. So this is the pH at which magnesium oxide is at equilibrium, right? But then look at this, at pH less than that, right? At pH less than that, you're going to have lower acid, right? And then you're going to have an increased, no, lower OH or lower base, and then we're going to have an increase in solubility, right? And then at pH higher than that is going to raise OH, and then it's going to decrease the solubility, right? So the pH, or the addition of an acid or base, it's going to increase or decrease the solubility. So make sure that you know how that changes, because it's different for a base and an acid. So if you have a base that is insoluble, an acid will dissolve it, right? And then a base will make it even more insoluble. If you have a acid that is insoluble, a base will dissolve it, and an acid will make it even more insoluble, right? So I think that is a good place to stop. We talked about a lot, but that is why we have a video, so that you can come back to it. That is why we have the book and the PowerPoint, so that you can read it and try to find another way to understand it. And that is why we have a lot of practice questions, homework quizzes, so that you get more chances to practice and understand this. And that is also why you have me, so that you can reach out to me if you don't understand. So that is it for this chapter. I will see you in the next one. Bye bye.